let's look at classification task. So we're going to get some data here. This is the MNIST data, which we're going to use in quite a few of these projects. Let's see if I can. Gonna make you log in again. I don't know a better algorithm here. All right. Perhaps this is Google's way of discouraging you from using it so much. Anyway. All right. All right, this is going to get the MNIST data, and what this data is handwritten digits written down by people who did the American Census. So they are just digits from 0 through 9. And I'm going to get to where we can view them here. All right. Got to wait for it to finish running the previous ones before I can run these, but shouldn't take too long. There we are. That first part's done. This is just going to show me the data. The data is pixels for images, 784 pixels for each image, and there's 70,000 of them. And then the labels. This is labeled data, so 5, 0, 4, and so on. Tells you what the right answer is. And here's what they look like. I'm going to print 100 of the images here so you can see what we're working with. Okay, so there they are, handwritten letters, handwritten numbers, so most of them are nice. Some of them are sort of bent over and broken like this, so you might have trouble telling if that's a 5 or a 6, and so on. And we have labels, so we know the right answer for all of these. So we can train a machine learning model to do that. So we make a training set of 60,000, and test set is going to be the remaining, which I think is 10,000. All right. And now we're going to make binary data. First, we're going to make a binary classifier that cannot sort it into 10 categories. It's just going to sort it into 2 categories, true or false. So we're going to take all the 5s and call them true, and everything that's not 5, we're going to call it false. So we're going to simplify the problem to make a simple model for starters. So that's all this is going to do. It's going to create a model where it labels the 5s, and so there's 5,400 5s, and there's 54,000 not 5s, 10 times as many as you'd expect. So I have a training set and a test set of binary data to classify, and now I can make a model just like before. In comes the data, I separate the pixels and treat them as independent values, which I mentioned before is probably not very intelligent, considering that you'd be a lot better off to retain information about whether pixels are near each other or not, and actually detect high-order features like lines and stuff, but we're not doing any of that. We're just treating them as input data. We're not even going to have a hidden layer. We're just going to take all the pixels and then feed them to the output. We're going to have an output that determines whether it's 5 or not 5, just by doing some kind of linear combination of the pixels. So we train a binary classifier, which is here. And there it is, going through a few epochs. Notice the loss is going down, 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 1100 and 800. So it's going through steps, adjusting all those weights to have less errors. And after it goes through enough epochs, it will stop. Now you can tell it how many epochs to go through by guessing. What's another technique is to just go until it gets worse and then stop, because that's apparently where you hit the bottom. That's a common way to stop it. So here's the loss going down to 70, 77, and then it went up. So since it went up, it stopped. So it ended up at 239 epochs. And so now here's the first 3 predictions. 5 is really 5, that's true. The next 2 are not 5, so they're false. So the first 3 were correctly predicted. And now you can measure the accuracy of your model. And you need a little bit of statistics to get a good measurement of the accuracy of such a model. And this is going to give me scoring. It's going to give me 3 accuracy numbers. And those, what this is doing is cross-correlation. It's going to train on 2/3 of the test set and try to predict the other third, and then it's going to do that 3 times. reshuffling the 3 bits. That's cross correlation. So you get 3 measures of efficiency. It's 95%, 96%, and 96%. So that sounds pretty good until you realize 90% of them are not 5. If you just said not 5 all the time, you'd have 90% accuracy. So 96% is not as great as you might think it is. But anyway, a more precise way to analyze it is to have the whole confusion matrix. So let's get that. Okay, and confusion matrix. I'll just go to my example here. All right, there's my confusion matrix. So these are not 5s correctly assessed as not 5s, and these are 5s correctly assessed as 5s. And these are not 5s incorrectly labeled 5s. So that happens 687 times, and these are 5s incorrectly labeled not 5s. So you can see it's very biased. The not 5s are very unlikely to be incorrectly interpreted as a 5. This is 600, and that's like only 1% of them are wrong, but almost 50% of the 5s are incorrectly labeled as not 5s. So the error is not simple. It's dependent. The error is uneven that way. And so there are various measures. There's one called precision and one called recall, and then there's an F1 score that combines the two to try to boil these down to a number. And you can get those various measures of it. And the point is, the model doesn't put out a true or false. The model puts out a signal, and you can choose the threshold. If the signal is high, it's likely to be true. If the signal is low, it's likely to be false. So you can adjust that. If you move the threshold real high, then it will almost never incorrectly give you a true result, but it will have a lot of false negatives where the true data is incorrectly classified as false. And this is the same as biometric sensors. I remember teaching this for years. If you have a biometric sensor like a thumbprint reader, you can set the sensitivity really high so it's really picky. So now nobody unauthorized will get in, but your authorized users will frequently be rejected because their finger isn't completely matching the example. You can also set the threshold low, so your authorized users always get in, but now some authorized users will get in. That's what's going on here. You can adjust this threshold, and you can plot the result of it, and so precision and recall as a function of threshold go like this. And you can just see how it's varied by the threshold. So that's an issue with classification. And then you can do multi-class classification. Now, in order to do this, you have to take binary classifiers and turn them into multi-class classifiers. And the way we're going to do it here is with the 1 versus 1 strategy. So it's going to make all possible, it's going to compare 0 to 1, 0 to 2, 0 to 3. There's going to turn out to be 45 binary classifiers here. And then you combine the output of all of them to determine how accurate it is. It's going to have only 3 failures in a test set here. The other technique is 1 versus the rest. You have the one we just made that was 5 versus not 5. So you make one for 0 or not 0, 1 or not 1, 2 or not 2, and you end up with only 10 models that you have to train, and then combine the outputs to get the classification. And so there's various ways to do this classification. And you can do it with cross-validation, and then you can make the confusion matrix of the result, which is now pretty complicated. This is the true label, and this is the predicted label. So the diagonal are the ones it got right, and here's the ones it got wrong. And you can see it's not even likely to make every mistake. Like here's a pretty high number, 13. It is very likely to predict an 8 when the input was actually a 1. And it's pretty high to predict an 8 when the input was actually a 5, and so on. So this is a way to represent the actual function of your model. And all right, so that's the classification one. And I'm going to talk about support vector machines next.